All right, so today we've got Zonia Menendez, who is a grad student at Wesleyan University, graciously coming to our 403 lectures to give us a talk about an intro to elliptic curves.
Hi, everyone. Yeah, as Noel said, my name is Zonia Menendez. I'm a fifth-year grad student and at Wesleyan, which is Noel's alma mater. And I actually know Allison too through the EDGE program because I was a mentor while she was an algebra teacher then, a professor then. So I want to thank both you, Noel and Allison, for putting this together and for the invitation. In my research, I research elliptic curves and kind of more complicated. I look at like modular curves that give us information on elliptic curves. But today we're just gonna talk about elliptic curves, in addition on it, and pretty much the group structure on it, but you don't need to know any abstract algebra to be able to do this. I'll define the things as we need them. Yeah, and please feel free to interrupt me if something's unclear, if there are any questions. So we'll start with a definition. And some of this I have like written up already just to save some time, but I hope it won't be too fast because I will be writing some things down also. So our definition of an elliptic curve over the real numbers, which the real numbers will denote as this like blackboard bold R right here, is the set of solutions, x and y, both in R, so that this equation holds, y squared equals x cubed plus ax plus b, where a and b are real numbers, and so that this weird formula, 27b squared plus 4a cubed, does not equal 0. And we'll talk about this, as you can see, with my prompted question below, as well as a point that we call the point at infinity, and I'll denote it as this big O here. And so we want to talk about why do we insist that this 27b squared plus 4a cubed not equal 0? And the whole point is that it guarantees that we have no repeated roots. So let me write that down. And the reason we want this is so that we can define a tangent line at each point of the curve. And so sometimes I'll say curve, elliptic curve, I'll call it E, or I'll shorten it as EC for elliptic curve, but they all mean the same thing. So let's start with some examples. We have these equations here. The first one, y squared equals x cubed minus x plus 1, where here a is negative 1 and b is 1. So we can calculate that this equation does not equal 0. And for our second equation, we have y squared equals x cubed minus x. And again, we can verify that 27b squared plus 4a cubed does not equal 0. In the first case, it's kind of hard to factor out this equation on the right because we have two complex roots and then one real root that's not like an integer or like a really nice number. So I'm just going to leave it as is. But in the second equation, right, we can rewrite it as, let's see, I have it written down so I don't mess it up, x times x minus 1 times x plus 1. So this tells us the right-hand side is going to equal 0 when x is either 0, positive 1, or negative 1. And if the right-hand side equals 0, that tells us y squared equals 0, and so then y is 0. So we can find, so we know already 3 points on the curve, the points 0, 0, 1, 0, and negative 1, 0. And usually actually drawing these elliptic curves can be kind of tricky. So a lot of people just like throw it into Sage, Mathematica, things like that to give us a better idea of what these curves look like. So I've actually cheated and already have them drawn. So here, right, maybe I'll use a blue. And here are the, when the right-hand side is 0, so y is 0, and here's the one real root here. And we do have to to other places where the right-hand side is equal to 0, but we only want solutions in R squared. I think there's a question. Oh, okay, cool. Just making sure. I usually miss all the questions in the chat, so I'm trying to be good about actually looking at it. Yeah, so in our case, because we're looking only for X and Y real numbers, we're only gonna have the case that we either have 3 real roots or 1 real root, because our complex roots always come in pairs. Okay, so let's look at some non-examples. So we have these equations here. And let's see, we can actually factor this out pretty nicely to have x minus 1 squared times x plus 2. And then, right, this is x cubed. It's kind of weird to write it this way, but this is a good way to realize what the roots are. We have x minus 0 cubed. So you'll notice in both of these, we'll have a repeated root on the right-hand side because this integer here is more than 1, right? And that's going to give us some issues. And the whole point is that we want to be able to look at the tangent lines at all these points, because that's going to help us think about what, or define our addition on the elliptic curve. So I have some pictures below. Oh, move this up. Right, and the points that are giving us the issue, let's see, did I flip these? I did flip these, so this one corresponds to the other equation. And you can just tell by the zeros. All right, so this point here and this point here are the bad points on this curve that it's not an elliptic curve. Right, you'll see here, this is kind of like, oh, that's not the pointer. Oh, it is the pointer. We have that it's kind of like self-intersecting, right? We go through the curve here once and twice again through that point. And if you try to look at the tangent line at that point, it's going to be different depending on where you're coming from on the curve. So that's going to give us an issue. Yeah, and this corresponds to the point 1, 0. And so this point here, 0, 0, also gives us some issues because it looks like it wants the tangent line to be horizontal, but that can't be right. So that means that our derivative at those points don't exist, so we don't have tangent lines. Okay. Okay, so far, do we have any questions on the definition or any of the examples that we have?
I have a question.
Mm-hmm.
Okay, so like I'm looking at this and I am super excited that like not being on an elliptic curve is like corresponding to not having a derivative. Is there a way, like, is there a reason that the derivative is important here? I don't think that I don't know if I asked the question well. Does not having a derivative always mean at some point always mean that this thing is not an elliptic curve?
Yes, and
Okay,
it tells us
okay.
that we have a repeated root as well. So we get
Okay.
like all those things at once.
Oh, okay.
Yeah, and yeah, I'll just leave it at that. So one thing I forgot to point out from our actual examples above is, let's say we had a point, let's call it P, where the coordinates are x naught, y naught. Can anyone tell me if we can find another point that kind of corresponds to that point or is like similar to that point in any way? So let's say I chose this point here as my P. So maybe let me say, what if we kept the x not the same? Is there another value for y that will make this equation still be true? Any takers?
Would it just be negative y naught?
Exactly, exactly. We get negative y naught, right? And you'll notice in all of these images, we have this symmetry, oh, that's not lined up, on the x-axis. So as soon as you have a point, x naught, y naught, we also have the point x naught, negative y naught. And we'll see it in our addition, this is actually gonna be the inverse of that point. So this is really negative p. That's how we'll think of that. Okay. So we talked about not wanting a repeated root and talking about like the solutions to this elliptic curve, but we also had that third thing that we wanted a point at infinity. So this is kind of a weird concept, but so we should talk about it. So the point at infinity, it is not a point on the plane, but seen as the upward direction. So if you had a point on the curve and you wanted to make a line through the point at the curve and the point at infinity, it's just going to be a vertical line through that point P. So if I wanted a point through P and through the point at infinity, it'll be exactly the vertical line because it's supposed to be seen as like that upward direction. So it's just supposed to be like a peak point above that's not actually on the plane. And when you do this, you'll get P and negative P on that line as well as in the point at infinity. Okay, so let me write that last part down. So if we draw a line through P and the point at infinity, it is the vertical line through P and negative P. Okay, so as I said earlier, we kind of want to talk about an operation that we'll call addition on an elliptic curve. And this is going to make it a group. So we want to think about addition maybe somewhere else that we're more familiar, like the real numbers, and think about what properties about that do we want to transfer into our elliptic curve example. So some properties that we have that I have already written down are, so we have the real number 0, which is supposed to be our identity, because for any real number x plus 0 or 0 plus x will give us back that real number x. So we want a point on our elliptic curve that works like the identity. The second thing we want is that for any real number x, we have a real number y, so that when you add them together, you get back 0. And this y in the real numbers is negative x, because x plus negative x gives us 0. So we'll call this the inverse of x. And we've actually already seen this. We already talked about what negative p looks like. And so we'll want to instill in our definition that p plus negative p will equal 0. And then the last thing we want is that for any two real numbers, x and y, when you add them together, you get back a real number. So in our case, we want to take any two points on our elliptic curve. We want to end up with another point on our elliptic curve. And this is called closure. There's something else that you need to do with groups generally, which is show associativity, but we won't talk about this. And I think a lot of people usually tend not to want to talk about associativity. Okay, so let's talk about some facts about elliptic curves, and this is going to help us talk about this addition on elliptic curves. It'll be kind of a natural way after we have these facts laid out. But before I continue, do we have any other questions? Okay, I'll take that as a no. So our first fact is that any non-tangent line through 2 points on E, our elliptic curve, intersects one more point. And this could be the point at infinity. Okay, and here we can look at an example. Let's see, we want 2 points that are, when you make the line through them, it won't give you a tangent line through of the curve. So let's see, let me pick this point here, P, and this point here, Q. And so we know, or we're told that, let's choose a different color, that the line through these 2 points will intersect the curve at one other point, right? Let's call that point R. Okay, and so we'll use this later on when we actually define what we want our addition to be. Okay, so second fact that we have is the tangent at infinity, at the point infinity, to E does not intersect the elliptic curve at any other point. Okay, and then the last thing that we have is that any other line tangent to an elliptic curve, tangent to the elliptic curve at a point on the curve will intersect the curve at one other point, at exactly one other point. Okay, so here, let's look at this. And so we have some various ways we could have tangent lines. So this, let me get this one over here. Right, there's this weird point here that has a tangent line, I guess also corresponding here with the vertical line, right? But we can also have non-vertical tangent lines that look something like that. And it will intersect the curve at exactly one other point. And the way we think about the point it intersects in this case is, again, the point at infinity. So it intersects at this point here and the point at infinity, and the tangent line at this point intersects at exactly one other point that is right here. Okay. So now we want to define what our addition on the elliptic curve is going to be. Let me maybe move this up since we have more space. Okay, so we're going to take the point at infinity, the special point that we have. It will be our identity. So just like 0 in the real numbers, we can say for any point P on an elliptic curve, 0, or the point at infinity plus P, or in the reverse way, P plus a point at infinity will give us back P. This is what we want to be true because we want the point at infinity to be our identity, right? So we can deduce one other thing about this. Since the point at infinity is another point on our curve, we can say that the point at infinity plus itself will also be the point at infinity. So the point at infinity is exactly its inverse. Okay. And we've already talked about this fact a couple times, but we'll get the negative, or maybe I'll say the inverse of P, a point on the curve. Is denoted with a minus sign, and we write x negative y, right? So something that we'll want to be true is p plus negative p is going to equal the identity. And that's really gonna help us decide what we want this addition to be. Okay, so this third thing. Now, if you have two distinct points on the curve, P not equal to Q, these 2 points, then we've talked about how the line through P and Q if the line is not a tangent line to the curve, it will intersect the curve at another point, call it R, right? And we actually had this up here. So let me, actually, I don't know if I can't move that. So I'll redraw this here. So this is for P not equal to Q and the non-tangent case. So let's see, pick P and Q. Just want to make sure it ends up on my drawing. Something like, oh no, I didn't. So maybe I'll draw the line first. But this should work for any 2 points you pick. I just didn't draw enough of my curve. Right, so if this is the point Q and this is the point P, we know it intersects the elliptic curve at one other point. And we're gonna look at negative R. So we're gonna reflect it over the x-axis, and we're gonna define P plus Q to equal negative R. That's how we're gonna define this case where P does not equal Q and we don't get a tangent line. Now, in the case that we have a tangent line, so still P not equal to Q, but the line through P and Q gives us a tangent line. Right, we can think of this point here, and we'll look at the tangent line at that point. Something like this, right? It'll intersect the curve at exactly one other point. And here we'll define, so if I name this P and I name this Q, we'll define P plus Q to equal negative P. So this one's kind of weird, right? So we chose the point that the line was tangent to the curve at that point. So it has to be this point here. Okay, and so now we have to think about what happens if P equals Q. So you're trying to add a point to itself. Let me move this down a little. Maybe I can't. Let me move it over then. If P equals Q, again, we'll have our 2 cases where, or actually we don't have 2 cases, right? We're gonna take this here. Let's say I pick this point here, P. And I want to know what P plus P is. So what we actually do is draw the tangent line at that point. Look at where it intersects and then reflect it. So here, P plus P is going to equal negative Q, right? This is another way of writing 2P. Things look a little bit different when the line is a vertical line, right? So for like this point here, the tangent line of the curve at that point is vertical, but it intersects the point at infinity, right? So we'll say P plus P equals the point at infinity in that case. So we kind of want to think about, why did we choose this way of writing our addition? And in particular, I'll talk about this case here where P does not equal Q, and we're looking at the non-tangent, when the line through P and Q is a non-tangent line through the curve. Okay, so the answer to this, or one answer to this, is because we want the point at infinity to act as our identity element. So that means for any point P on our elliptic curve, we want P plus the identity element, or the point at infinity, to equal P. Right. So we want to think about two distinct points. I guess actually this is the tangent one. Oh no, okay. So we have something that looks like this case here, right? Where the point P, the line through the point P and the point at infinity gives us this vertical line, which is going to intersect. This one's a weird one, but it's going to intersect the point negative P, right? Maybe I could instead, let me copy this. Maybe I'll pick a different point. Okay, so maybe instead, let me pick this point here. So what I would do in this case is think about the line through the point P and the point at infinity, which is going to be this vertical line, right? And so the other point that it intersects is going to be the point negative P, right? So so maybe let me call it R, even though we know that it's negative P, right? If instead I said P plus the point at infinity would give me R, that's the same thing as making it equal to negative P, which would break the fact that the point at infinity is our identity element. So instead, we want to think about adding these 2 points by looking at the inverse of the third point that the line intersects. So we want this to be negative R, which is equal to P, which is exactly what we wanted it to be here. So this is one of the reasons why we picked the negative point that runs through that line, is because we want the point at infinity to actually work as our identity element. So with all of this, we can say that we have addition on our elliptic curve, and so that gives us a group. So there's a lot of like rich structure that you get with this group. And for those who might have seen abstract algebra before, a lot of things people like look at are the torsion points of this group and things like that. And something like modular curves can study the torsion point of elliptic curves or classes of elliptic curves all at once, which is really nice to do. And just to close out, some applications that I know of are cryptography. You guys might have heard of like the whole Bob and Alice example that they always have, but that's usually with like prime numbers and being able to find like prime decomposition of numbers. But in this case, it's about being able to find multiples of points on elliptic curves. That's how you could use elliptic curves with cryptography. And a second way this could be applied, that was applied, was with Fermat's last theorem, which states that there's no integer solutions for x to the n plus y to the n equals z to the n for n greater than 2. And this was like a big unsolved, it was a conjecture for over 350 years. And something like elliptic curves and modular curves and a lot more, there's a lot more into it, but this is one piece of it, that they had to study elliptic curves to be able to have the machinery to be able to prove that theorem. Okay, so that concludes my talk. Thank you again to all the organizers and everybody here. Thank you.